Hey everyone, so today is our last lesson for Unit 1, which is just the circuit's basics. This last lesson is about brute force. So brute force is a less known method. It's definitely a more math intensive method to solve circuits, especially circuits that include loop analysis with a super loop. So right here we have this loop that we did back in one of the loop analysis lessons. I think lesson 14 or 15. I can link it up here, or you can go check it out on the playlist. But as you can see right here, we drew a super loop and it was super simple. We just had one equation, L1, big L1, and we got 7/8. Now for brute force, what we do here is we treat every single loop as unknown and introduce a new variable, okay, or a few new variables, okay? So we increase the number of equations that we have to solve something so that we don't have to think about this giant super loop, okay? So let's get started. The first loop that I'm going to choose is I1, like this. And then the second loop I'm going to choose is I2. And we're not assigning 3 amps here because we're going to use that for something else. And then we have another loop this way, I3. Okay? Now, the cool thing about brute force is all of these current sources are going to turn into a voltage difference, okay? So the arrow is going up, so we're going to do plus here, minus here, and we're going to call this one V2. Okay, this one I want to call V1 right here. That's plus and V1. So now we're going to treat this whole branch as a power source or a voltage source or some voltage difference. Voltage difference is actually more correct, okay? So we are just going to solve this like normal. We are going to find loop 1, and loop 1 has 2I1 in it, plus 1, plus V1, because we're treating it as a voltage difference, plus 3, and notice what's in that resistor is I1 minus I2 equals 0. Then we're going to simplify it down. And we get 5I1 minus 3I2 plus V1 equals -1. Okay. We're going to go ahead and do loop 2. So loop 2, we can start with the voltage, the unknown voltage, negative V2, plus 3, and then remember I2 minus I1, plus, and we've got 1, and we've got I2 minus I3, because I3 is going the opposite direction, equals 0. Simplify this down. And we get -3I1 plus 4I2 minus I3 minus V2. Last loop. It's loop 3. We're going to have, let's start from the 2 ohm resistor. Remember here we have I3 going through this 1 ohm resistor and I2 going through the opposite side. And minus V1 into the back of the V1 voltage difference equals 0. Simplify it. We get -I2 plus 3I3 minus V1. Now notice, we have 5 variables, okay? Yep, we have 5 variables, but we only have 3 equations. So where are we going to get the other 2 equations? And this is where the brute force part comes into play. Remember that we never took into account what we were actually given, these currents, okay? So what we're going to do is we are going to perform KCL at the nodes at which these currents go into, okay? So first, we're going to look at this node right here. We're going to say we have 3 amps going in. And then coming out, what do we have? Well, we have I2 going out of the node, and we have I1 going into the node, okay? And then right here we have I1 going out of the node, okay? And so that's one of our KCL equations. So what I would do here is I'd say KCL 1, circle that, and we do -3 plus I2 minus I1 plus I1 equals 0. And we've proven that I2 equals 3. Okay? And this is like pretending that, oh, we're not going to assign 3 amps to something arbitrary, okay? So now we have I2. We've eliminated another variable, one variable. Now let's do KCL2 from the other current source. So right here, we have 4 amps going into this node. We have I3 going down, and we have just I1 going here. And so we get I3 minus I1 minus 4 equals 0, okay? Or we can say I1 minus I3 equals -4. All right, so now we have 3 equations, 5 equations, 5 unknowns. We can go ahead and solve. Now, you can just straight up put all of this into the calculator, or you can plug in I2 already, but I think for the sake of just showing all of these equations out together in a matrix form, I'm going to go ahead and just solve it all by plugging into a calculator. Okay, so to help me not get confused, I like writing out my equations like this, you know, with columns like this, and then we're going to write this into a matrix form. And there we go, we have it in matrix form. And for those of you who have taken linear algebra, you may be able to find some beauty in this. It's definitely very interesting that we're expanding this out, whereas as opposed to just using one equation right here, right? We've expanded this out to a 5x5 matrix, right? And we're also finding 2 new values, v1 and v2. Okay, so let's go ahead and plug this into the calculator. Oops, I just realized I made a mistake. This is supposed to be 3 right here. And for our final results, we get I equals -0.125 amps. I2 is equal to 3 amps. I3 is equal to 3.875 amps. V1 is equal to 8.625 volts. And V2 is equal to 8.5 volts. And we are not yet finished because we are being asked to find this guy right here. So once again, we are going to say that we have 4 amps going outwards, right, plus I3 minus I1, okay? We've got I going inward, so we're going to leave that guy alone. Then we've got on the other side, we've got I1 going out, right? And we've got I2 going in. Wait, sorry. We've only got 4 volts going out this way. And so now we get I1 minus I2 plus 4 minus I equals 0. And we take this I on the other side. So we get negative 0.125 minus 3 plus 4 is equal to I is equal to 0.875. And so the reasoning here is that we've got only 4 amps going out this way, right? And then we've only got I1 going out and I2 going into the node, and then we've got I. So remember to make sure that you're only looking at the currents going in and out of this node, okay, when you're trying to find I. And so writing it down here more clearly, we've got I1 going out of the node minus I2 going into the node plus 4 going out of the node minus I is equal to 0. And then I is equal to I1 minus I2 plus 4. And we proved that to be 0.875 amps. And here's the exciting part. 0.875 amps is the same thing as 7/8. Okay? So look how we expanded this and we introduced new variables, right, to solve the exact same problem. Okay? Now, you may be wondering, why the heck am I going to do this, right? This was a lot more math. I even got confused doing it when I was doing this node right here. Why would I do this? Well, tell me, what if you were asked to find V2 right here, okay? And it asked you to do it with loop analysis. How would you do it? Well, you would do it with the brute force method, okay? The brute force method is literally just combining nodal and loop analysis in some form or fashion. So there is a brute force way for nodal analysis, and that would just be turning a voltage source into a almost current source. If you like in that branch, you could say it's I1, I2, I3, etc., and you do the opposite. So that is why you would use brute force, okay? In this case, it was easier to do a super loop, and it also avoids using a super loop. Like if you couldn't think of how to do a super loop, right? In a super loop, you avoid these current sources, right, in your big loop. But in the brute force, you include your current sources, okay? So yeah, that's how you use brute force. We're going to do one more example, and that'll be it. Okay, here's our next problem. We're going to solve this with brute force. So the first thing that we're going to do is label our first loop. Okay, and our first loop is I1. And in our second loop, I'm going to do it this way, arbitrarily, I2. And then I3, arbitrarily. And we're going to make 3 amps look like this because the arrow is pointing down, so our positive is going to be pointing down as well. And then we are going to go ahead and solve this, solve each loop, or make an equation for each loop. So we've got loop 1, and that is just going to be -6 plus 2I1 plus 6I1 plus I2, because they're going in the same direction. I chose them to go in the same direction. Plus 3I1 plus I3. Once again, I chose them to go in the same direction. So we're going to simplify this, equals 0. And we're left with 11I1 plus 6I2 plus 3i3 equals 6. We're going to do loop 2 now. In loop 2, we've got -4, right, stepping around, plus 6 times I2 plus I1 minus V this time plus 2I2 is equal to 0. And simplify it. And we've got 6I1 plus 8I2 minus V equals 4. Okay? Last loop, loop 3. First, we're going to go through the 3 ohm resistor. I3 plus I1 minus 2 plus 4I3 plus V. We're going to simplify this. And we're going to get 3I1 plus 7I3 plus V equals 2. Now we have to perform our KCL. So I'm going to go ahead and you can do KCL here or you can do it here. Okay. I am going to do it here. Okay. So we've got I3 going in, I2 going out, and straight up 3 amps from this way. So we've got 3 going out, 3 going in, plus I2 minus I3 equals 0. And we get I2 minus I3 equals 3. Okay. We have 4 equations, 4 unknowns. Let's go ahead and put it in a matrix. There you go. And I'm not going to go ahead and put it in matrix form. I'm just going to go ahead and solve it out. And we get I1 is equal to -3/14 amps. I2 is equal to 27/14 amps. I3 is equal to -15/14 amps. And V is equal to 71/7 volts. Okay. And what are we looking for here? We are looking for this guy right here, which is equivalent to I1. So simple this time. So I1 is equal to -3/14. Okay. Now I think for completeness sake, we should go ahead and do it the regular way. Okay, with the super loop. Now the reason why I want to do this with a super loop is so that I can prove a point to you guys. Okay. So first of all, think about this. What is the first thing we're going to do? Well, the first thing we're going to do is assign the 3 amps to something arbitrary. Okay. Now, how do we do this? We can't do this because we'd be counting this 3 amps. So that's a no-go. We can't do this either because that would also be counting 3 amps. Okay. But we can do this, right? We can do this, right? Or we can do this and this, okay? Now, I already did solve this out, and I just realized that this is probably the more efficient way. But I went ahead and did it this way, and I'm going to show you how these super loops can get a little bit complicated. Okay. So let's go ahead and start it. L1. So we've got negative 6 plus 2i1, right? Plus 4 plus 2. And now what is in this guy? Well, we've got I1 and we've got I2 in it, okay? Because I2 is going this direction, okay? And we've got 4. Now this one, be very careful with this one. We have not just 1, not just 2, we have 3 currents in it. We have I1, I2, and 3 amps, okay? Plus 2 equals 0. And simplifying this down, I already have it written, so I'm not going to go through all the math, where I hope that this is simple enough and we've done enough practice problems so that you can go ahead and do it. But you're going to get 8i1 plus 6i2 equals negative 12. Okay? Now loop 2. So loop 2, also be careful. We start with plus 4 volts. Plus 2 times I2 plus I1, because we've got I1 going in there as well, plus 4 I2 plus I1 plus 3, plus 2 plus 3, and also be careful here, we have 2 currents, I2 and I2 and 3, and I'm running out of room here, so plus 6i2, okay, equals 0. And simplifying this guy down, we get 6i1 plus 15i2 equals negative 27. And solving this out, we get, lo and behold, negative 3/14 amps. Okay? And for I2, negative 12/7. Okay? And check that out. We've got I1 and I1 to be the same. Now, I2 and I2 are different here because I2 counts as something different from this I2, okay? This I2 is accumulated current all the way through this loop, whereas I2 is accumulated current all the way through this loop. So those are going to be different. But because I1 is independent, like right here, we're going to get the same answer, and we don't have to do any mental gymnastics. Now tell me, would you have rather done the super loop, or would you have rather done the brute force in this case? Right? I'm not sure, actually. Both are pretty tedious. You still have to make some pretty nasty loops. You could have made this simpler by doing this, but this second one still had a lot of stuff to take into consideration, right? So this is simply just another way to solve circuits. Highly recommend practicing it, because if you practice this, then you will truly understand loop analysis and even nodal analysis a lot better. Okay, that is the end of this unit. Next unit, we're going to talk about things called op amps and voltage dependent power sources, voltage dependent current sources, current dependent voltage sources, etc., etc. And then after that, we're going to do another unit, and that one is going to be with capacitors and inductors. Okay, so stay tuned for that. I'm going to upload a video with tons of practice problems, but that probably won't come out in a good bit, because I want to make sure that I make quality practice problems for you guys to solve with me. And yeah, so if you find any other way, easier way to solve this, please solve it that way as well, as long as you get the same answer and you stay with the coordinate system, because if you deviate from your coordinate system, you will mess up. Okay, everyone, that's it for this video. See you next time.